Okay, part B. Part B says use a left Riemann sum, with the 4 subintervals indicated by the table to estimate total amount of water removed. That means we should not be focusing at all on how much water is there or on how much water is being added. We're only focusing on how much water is removed during the 8 hours. So the fundamental theorem is right here, and it tells us that if in this example, where R is the rate at which water is being removed in liters per hour, then if we integrate that rate, the integral will tell us the amount of liters removed for that time period. You can see that because right here, you're going to be multiplying R of t, which is liters per hour, and you're multiplying that by a amount of time, and you end up with liters. That's why when you integrate the rate at which water is removed from the tank, the integral calculates the total amount of water that was actually removed. So you're integrating liters per hour, and you're calculating a number of liters. So that's all I have to do. So I write down the integral, always, and then I do the left Riemann sum. So the subintervals are as I'm showing now. I go to the first subinterval and I pick the value of R that is most left in the subinterval. That's the 1340. That gets multiplied by the dt, or change in time, for that subinterval. That change in time is from time hour 0 to hour 1, so that's 1 hour. Which is basically where we're making the assumption that for that entire hour, we were losing 1340 gallons per hour. So that multiplied by 1 tells us that we would have lost 1,340 gallons during that hour. That's how much water would have been removed. That's not really what happened, of course, because the rate actually changes within the hour, but that's our estimate, our left Riemann estimate. Then we go to the next subinterval. We pick the value of R on the left, and now we assume that R has that value for an entire 2-hour period. That's why we're taking 1190 multiplied by 2 to approximate how much water is removed from the tank during those 2 hours. We continue that process for the next 3 hours, from hour 3 to hour 6. We're going to assume that 950 gallons per hour are removed. That's why we're multiplying the 950 by 3 to approximate how much water is actually removed. That's what you're always doing. We're taking a rate and we're multiplying by an amount of time, just like the integral says. A rate multiplied by an amount of time, that's going to give us a number of liters of water removed for that time period. The way this was scored is they expect to see your Riemann sum written out. You don't have to keep going, though. You don't have to go all the way to the 8050 number. I recommend you stop with just the red box or the blue box. They're the same thing. You get 2 points basically for doing that. So 2 points so far for doing the Riemann sum. Is this an overestimate or an underestimate of the total amount of water removed? Well, notice, they told us R was decreasing. So the values of R are always going down. That means every time we pick a value on the left of a subinterval, so here's our subinterval, we pick the value that is on the left, that's going to be more than the actual rate during that hour. And then here we pick this value on the left from hour 1 to hour 3. That's more again than the rate will be during that entire 3-hour period. So we're definitely getting an overestimate. All they expect you to say is, this is an overestimate because R is decreasing. That's all you have to say. Here's another example of what you could say. R is decreasing, so the left Riemann sum is an overestimate or an overapproximation. and that was one more point for a total of 3. So 3 total points on part B.